Hi everyone, I'm Roderick de Schaetzen, and today I'll be talking about our ICRA paper titled Real-Time Navigation for Autonomous Surface Vehicles in Ice-Covered Waters. Consider the following scenario. Suppose we have a ship navigating across ice-covered waters consisting of a high concentration of sea ice. The direction in which the ship must move is usually made clear based on the ice environment. For example, there may be a narrow ice channel formed by an icebreaker. The goal is for the ship to safely navigate through the ice. The problem we address is autonomous ship navigation operating in icy waters. There are two core challenges that are specific to this problem. One, the environment is potentially dense with obstacles, and two, the obstacles move in response to actions taken by the ship. We assume the ship is built to withstand some collisions with ice, meaning ship-ice collisions are permitted up to a certain extent. We can therefore remove the restriction of collision-free paths from the navigation framework. Our goal is to design an efficient navigation framework for a ship navigating through a cluttered ice channel while minimizing damaging ship-ice collisions. As a preview, here's a video showing a sample simulation trial using a proposed approach. We propose the following receding horizon navigation framework. To account for the large and evolving environment, we frequently replan a reference path and velocity profile for a controller in real time. Replanning is done over a moving horizon, which was illustrated by the orange dotted line in the simulation demo on the previous slide. We treat the ice as static when computing a trajectory, but we frequently run updates of the algorithm to account for ship-ice collisions and ice movement. We therefore enforce low planning runtime for each iteration in order to achieve high planning frequency. In the next slides, we describe the path planning module of our navigation framework. We use a state lattice path planning algorithm where paths are generated using a finite set of pre-computed motion primitives. We treat the ship as a 2D rigid body and adopt a unicycle kinematic model. A state lattice is generated by discretizing the plane into a uniform grid and the headings into uniformly spaced angles around the unit circle. We use Dubin's paths to define our motion primitives. The figure on the left shows an example set of motion primitives, and on the right we can see the sort of paths that can be generated by concatenating together different motion primitives. To evaluate the quality of paths, we propose a cost function that captures the severity of ship-ice collisions in terms of the energy transferred during the collision. Our collision cost aims to minimize the ship's kinetic energy loss from ship-ice collisions. We adopt a simplified model of a 2D inelastic collision model to model ship-ice collisions. With this collision model, the change in kinetic energy in the system is known, and we can solve for the kinetic energy loss for the ship following a few assumptions and simplifications. Observe that the function effectively penalizes collisions with ice that are head-on or involve large ice pieces relative to the ship. In the next slide, we describe how we use this function to define our cost function. To efficiently compute collision costs across an ice channel, we use a cost map representation of the planar environment. For a path planning task, the cost map is effectively a lookup table for computing the collision cost associated with a particular path. Each grid cell in the cost map is assigned a cost equal to the kinetic energy loss function described in the previous slide if the cell overlaps with an obstacle. The left figure illustrates how we define costs for a path, and the right figure shows a sample cost map where brighter colors indicate a higher cost. We validate our proposed navigation framework through simulation and physical experiments. Each trial consisted of navigating a ship across the length of an ice channel. In our simulation experiments, we validated the effectiveness of our proposed framework as a function of ice concentration. Two baseline planning algorithms were considered, which we refer to as straight and skeleton. Straight refers to planning a straight path parallel to the ice channel, and skeleton refers to the shortest open water path routing approach found in existing autonomous ship and ice work. The two figures here show the probability density functions of the ice mass from the ship-ice collisions that were logged across all trials in the 40% and 50% concentration ice fields. On average, the proposed approach collided with ice that was 24% smaller in mass than skeleton and 29% smaller than straight. We computed a running total of the kinetic energy lost by the ship due to collisions with ice, using the physics simulator. To better interpret this metric, we used the ship total kinetic energy loss in the straight trials to normalize the values for each trial. This means if a trial returned a normalized total kinetic energy loss value of 1, then we did no better than simply navigating straight through the ice channel. The figure shown here illustrates again the improved performance of our approach. Our mean and median are consistently lower across all 4 ice concentrations. We conclude with an overview of the experiments ran with our planet in a physical ice tank. We ran a total of 8 trials across 2 different ice concentrations. This series of tests proved to be the first successful attempts at fully autonomous navigation across the entire length of the ice basin in the National Research Council ice tank facility following partial successes during preliminary testing. The collisions that occur along the path seem to be consistent with our design decisions captured by a proposed cost function. Namely, we avoid larger ice flows and the ship generally collides with ice such that the ice is pushed off to the side and therefore the ship loses minimal kinetic energy. Thank you for your attention.